the union. Then all the pi are the partition of intervals. Their cross product is the partition of the rectangle denoted by p prime. Okay. Then p prime is a partition of our I, as I said before. Okay. Then and for every j in our partition P, our Pj, what's Pj? Pj is the Pj is the partition of J, and actually Pj as a partition of J is precisely the consists of the subrectangle taken from P prime by the construction of P prime. Our Pj here as a partition of J is precisely the partition of I P prime. P prime, the partition of I. Pj consists of all the subrectangle of P prime containing in J. Therefore, by our notation, this is Pj is contained in the P prime J. Okay, and so the difference of the upper and the lower sum of f, which is respect to the partition of J, that is our P prime J, will not greater than the partition of Pj, because P prime J is a refinement of Pj. They are not equal, but P prime J is the refinement of Pj. Okay, so by the relation of the upper sum and the lower sum, which respect to refinement, you refine the partition, the lower sum will decrease and the upper sum will increase. Therefore, we have this inequality, and the right hand side is less than epsilon by the construction of Pj. Pj makes this small less than epsilon. Then we sum up. We use the m to denote the number of rectangles in P. Then we the difference of the upper sum and the lower sum of f, which respect to P prime, is the sum of all j. This is a result we proved before. For the upper sum, this equals the upper sum of f, which respect to P prime j, and then sum up for j over the partition P. This is our previous result. Yes, this result for upper sum. And for lower sum, the result is also true. So which this result, we see that the difference of upper and lower sum, which respect to P prime, is the sum over all j from the partition P of the corresponding difference, which respect to P prime j and okay, and every term. Sorry, I should have a break here. Every such term is less than epsilon by this line. Okay, every such term is less than epsilon, and we use the small m to denote the number of rectangles in P. Therefore, we altogether will have m terms. So this is less than a given constant m multiplied by epsilon. Obviously, this is sufficient to conclude that f is integrable over the rectangle I. So this complete the proof of the if part of the theorem. Okay, we still need to prove that the equality. We still need to prove that having proved the if and only if, we still need to prove this equality. Okay, so to prove the equality, we take epsilon positive. Then for j, for every subrectangle j, we can choose a partition for this subrectangle denoted by PJ, such that the upper sum, the distance from the upper sum with respect to this partition and the integral over J is less than epsilon. Why this is true? Because this is the upper sum. Upper sum can approach the upper integral, which is actually the integral because our function is integrable. Okay, so this is true. So for every J, we construct a P prime as before. Using for the PJ, you write the component of PJ and take the union, and then the union is the partition of every edge of our rectangle I, and then taking the this determines a partition of our rectangle. Okay, so construct a P prime as before. Then we will have UF P prime J minus this J will not greater than the will not greater than this, because P prime J is the refinement of PJ. Okay, therefore we have this inequality, but this is less than epsilon. Okay, then our integral of f over the rectangle I, because the P prime is a partition of the rectangle I, obviously the integral, that is the upper integral, will not greater than any upper sum. But this upper sum can be written in this sum, in this summation. That is all. That is we use this result again. Okay, P prime and P prime J. Okay, use this result again. We have this inequality. We have this equality. But every this sum, by the previous inequality, every this sum will not greater than from this inequality, UF P prime J minus the integral is less than epsilon. Therefore, UF P prime J will not greater than the integral of f over J plus epsilon. So this will not greater than the sum of f over the integral of f over J multiply epsilon. But we have m rectangle in the partition P. Therefore, we have m epsilon here. Okay, so we have this inequality. The integral of f over I will not greater than the sum of the integral of f over J plus some constant m multiply the arbitrary constant epsilon. So let epsilon goes to 0, we obtain this inequality. Okay, because this integral and this sum does not depend on epsilon. Therefore, although this is strictly less than this, but when epsilon goes to 0, it might be equal. Therefore, we have a not greater than sign here. So working with upper sum, we have one side inequality we need, and working with lower sum, you will, using the same argument, you will obtain another direction of inequality. So this these two inequality prove our deserved result. Okay. So this is the additivity of the integral over rectangle. But until now, we only discussed the integral of function over a rectangle. We have not discussed the general domain, general integration over general subset of Rn. Okay, so that is the topic in our future lecture. Now we consider another property of the integral. So suppose f and g are integrable, and the f is not greater than g. The result is that the integral of f over the rectangle I is also not greater than the integral of g. So this is quite easy. As we said before, the integral, the upper integral can be approached by upper sum. The lower integral can be approached by a sequence of lower sum. So we regard the integral of f by as a lower integral. Okay, then we can take a sequence of partition of I such that this integral, the lower sum of f with respect to the partition pk. So this is a sequence of real numbers. If you approach the integral of f over I. Okay. Now, for every rectangle, for every subrectangle in this partition pk, the infiniment of f over this rectangle will not greater than the infiniment of the corresponding g over this rectangle J. Okay, because f is not greater than J, so the infiniment of f is also not greater than that of J. Okay, so this means that the lower sum of f will not greater than the lower sum of G with respect to the same partition. If the partition is different, we have nothing to say. But for the same partition, we have this inequality. Okay, but the lower sum of G with respect to any partition will not greater than the lower integral of G. That is the integral of G, because G is integrable. Okay, so we have this inequality. So using this inequality and combine the limit here by the property of limit, we see that the integral of f will not greater than the integral of G over the rectangle I. So this proves the monotonicity property of integrable. Okay. Finally, we study the linear property. Suppose f and g are integrable over the rectangle I, and a, b are two real numbers. So a natural question is that, how about the integrability of the linear combination of f and g? And if the linear combination is integrable, what's the relation between the integrable of the linear combination and that of f and g? Okay, so the result is that the linear combination is integrable, and the integral of the linear combination is the linear combination of the integral of f and g. Okay, so this is a very important property. Using this theorem, we can divide a complicated function into some simple function and compute the integral one by one. Okay, compute the integral one by one to obtain the integral of our original complicated function. So this is quite useful.